Hello, today we're continuing in our A-level physics revision series looking at nuclear physics. Firstly, a quick review from what we've learnt from previous videos. I said that in the very early days it was thought that the atom was just a simple, indivisible point, but that it was J.J. Thomson who showed that an atom was made up of different bits, positively and negatively charged, and that gave rise to the plum pudding or the current bun model, where the dough of the bun was the positively charged bit and the negative part of the bun was essentially the currents. But then Rutherford came along and showed that wasn't right. He took radium bromide, which is an alpha particle emitter. He put a detector to detect the alpha particles. He put a gold foil in front of the alpha particle stream, and he found that a very small number of alpha particles were reflected. And that gave rise to him saying that an atom is not made up like a plum pudding. It's made up of a very small nucleus with orbiting electrons such that the bulk of the alpha particles just go straight through, but only if an alpha particle gets very close to the nucleus does it get rebounded. And we've covered all of that in previous videos. Now we're going to look at what's going on in the heart of the nucleus. And what we've said is that that nucleus consists of differing numbers of protons and neutrons. And effectively it's the number of protons that determines what the element is. If you have just one proton in the nucleus, that's hydrogen. If you have two protons, that's helium. If you have three protons, that's lithium. And you go all the way up to 92 protons in the nucleus, that would be uranium. And one of the problems we shall have to tackle is how can all of those positively charged particles be in such a small space? Why don't they repel on the basis that like charges repel and self-destruct the nucleus? But first, let's get a feel for the size of the nucleus compared with the size of the atom. An atom, very roughly, is 10 to the minus 10 metres across. A nucleus, by contrast, is 10 to the minus 14 metres across, very roughly. In other words, 10,000 times smaller than the diameter of the atom. Put it this way, if an ordinary room in your house were representing the atom, then the nucleus would be a grain of sand in the middle. What is the nuclear radius? Well, you won't be surprised to know that the nuclear radius will get bigger as a nucleus gets bigger, and a nucleus will get bigger if it's got more protons and neutrons, which we call nucleons, in it. So what you actually find is that the nuclear radius, if you plot that against the total number of protons plus neutrons, will go up more or less in a straight line. And the radius is given by a formula R equals R0 times A to the third, where A is the total number of protons and neutrons. R0 is 1.4 Fermis, or 1.4 times 10 to the minus 15 metres. A Fermi is 10 to the minus 15 metres. Don't confuse R0 with the Bohr radius. The Bohr radius refers to the radius of an atom. We are talking about the radius of a nucleus. Now what we're saying is that the whole, or pretty much the whole of the mass of an atom, with the exception of electrons which are very trivial, the whole of the mass of an atom resides in the nucleus, and the nucleus is a very tiny amount of the atom. And that means that the density of the nucleus must be very large. In fact, if you were to pick up a teaspoonful of pure nuclear material, not atoms, just nuclei, that teaspoonful of material would weigh 500 million tons. Let's just do a quick illustrative calculation. We know that density is mass divided by volume. So if we take the mass of, say, a proton and divide it by its volume, assuming that it's spherical, is 4/3 pi r cubed. Well, the mass of a proton is 1.6 times 10 to the minus 27 kilograms. And you divide that by 4/3 pi, and now r is very approximately 10 to the minus 15. We'll not worry about the 1.4, let's just call it 10 to the minus 15 cubed. Now to simplify things, let's just assume that pi is 3. It's not quite, but it'll do. So now we've got 1.6 divided by 4, which is 0.4, times 10 to the minus 27 divided by 10 to the minus 15 cubed. 10 to the minus 15 cubed is 10 to the minus 45. If you bring that on the top, it becomes 10 to the plus 45. And if you multiply 10 to the plus 45 by 10 to the minus 27, you get 10 to the 18 kilograms per meter cubed. 10 to the 18 kilograms is a massive amount in 1 cubic meter. And that's why nucleus or nuclear material is so dense. Now let's ask why the nucleus is held together when it consists of positively charged protons that ought to be repelling one another. What could be responsible for keeping them together? Well, the first thing we know is that there is an electrostatic force, or sometimes called the Coulomb force, which is the charge. So if we have 2 coulombs, we take the charge of the charge of proton 1 times the charge of proton 2 divided by 4 pi epsilon naught r squared, where r is the separation of the 2 protons. And if you calculate that, it comes to approximately 2.3 newtons, but it is a repulsive force. It is pushing 2 like charges apart. Well, maybe it's gravity that's holding them together. We know that the gravitational force is equal to the gravitational constant times the mass of the first proton times the mass of the second proton divided by the distance between the protons squared. But if you put that in, you get 1.86 times 10 to the minus 36 newtons. In other words, and that's an attractive force, but it's so trivial, 10 to the minus 36, that it's nothing compared to this. And so the answer is that protons should not exist inside a nucleus, but clearly they do. And there must be a reason for that. And the reason is that there is a strong force which overcomes the electrostatic force. If we were to plot the force, this is the repulsive part of the force, this is the attractive part of the force. If I plot the electrostatic force, this incidentally is r, this is the separation between 2 protons. The further away the protons are from one another, the smaller the force. But as you bring the protons closer and closer together, the repulsive force increases and increases. By contrast, there must be a strong nuclear force that has a shape that looks something like this. Let me explain what I mean by that. The first thing is that clearly it must have an attractive force when the protons are very close to one another, and this is an attractive force, so it will pull them together. Secondly, this force must be greater than the electrostatic force. That has to overpower that, otherwise the protons will repel. Thirdly, even the nuclear force, this is the nuclear force, must become repulsive at very, very short distances. Otherwise, if it was still attractive here, then the protons would be squashed into one another. So you need a strong force that pulls them together, but not so strong that it crushes them into one another. So let's just summarise this strong nuclear force. Firstly, it must be greater than the electrostatic force within the nucleus. Secondly, it's short range. It only operates within the nucleus. Once you get beyond the nucleus, the electrostatic force dominates. The nuclear force therefore falls off very quickly. In the middle of the nucleus, it has to be very strong indeed to overcome the electrostatic force. But by the time you've got to the edge of the nucleus, it can fall off very quickly. The strong nuclear force must affect all nucleons, protons and neutrons, but at very, very small distances it must become repulsive, otherwise it will squash the protons and the neutrons together. The gluons are responsible for this strong nuclear force, as we shall see in the next video. If you want more information about the nuclear structure and nuclear forces, then you can look at my nuclear structure physics video, which gives you more information than you need strictly for A-level, but explains all this in a little bit more detail. J. Thomson, who showed that an atom was made up of different bits, positively and negatively charged, and that gave rise to the plum pudding or the current bun model, where the dough of the bun was the positively charged bit and the negative part of the bun was essentially the currents. But then Rutherford came along and showed that wasn't right. He took radium bromide, which is an alpha particle emitter. He put a detector to detect the alpha particles. He put a gold foil in front of the alpha particle stream, and he found that a very small number of alpha particles were... Hello, today we're continuing in our A-level physics revision series looking at nuclear physics. Firstly, a quick review from what we've learnt from previous videos. I said that in the very early days it was thought that the atom was just a simple, indivisible point, but that it was J. Does it get rebounded? And we've covered all of that in previous videos. Now we're going to look at what's going on in the heart of the nucleus. And what we've said is that that nucleus consists of differing numbers of protons and neutrons. And effectively it's the number reflected. And that gave rise to him saying that an atom is not made up like a plum pudding. It's made up of a very small nucleus with orbiting electrons such that the bulk of the alpha particles just go straight through, but only if an alpha particle gets very close to the nucleus